In the entire world of medicine, there are very few places that carry a weight of responsibility quite like an in vitro fertilization lab. I mean, this is not just another clinical space. It's a sanctuary where the very first spark of human life is cared for. And every single detail, from the air itself to the light overhead, has to be absolutely perfect to protect the most fragile thing you can possibly imagine, a developing embryo. So today we're going to break down exactly how they pull this off. We'll start with the lab's physical design, then move on to the invisible threats it has to guard against. We'll get into the really critical equipment, break down the literal recipe for life in the culture medium, and then we'll take a peek at what the future of IVF looks like. All right, so the very first line of defense for a tiny, developing embryo is the physical layout of the lab itself. And believe me, this isn't just about where you put the lab bunches. We're talking about designing a fortress of sterility, where the entire workflow is built to stamp out any possible risk of error or contamination. And to really get why this is so important, you have to see where the lab fits into the bigger picture of a patient's whole treatment cycle. The lab is really the scientific heart of this entire journey. It comes in at the most critical moments, right after the eggs are retrieved, during fertilization and culture, and for those huge final steps of either cryopreservation or transfer. Now, inside this fortress, the work is split into these super specialized zones. You've got the andrology area, that's all about sperm. Then the embryology lab for the eggs and embryos, and of course, cryopreservation for freezing and storage. But here's the thing, all these areas share the same strict design rules. They're aseptic, meaning sterile, and you won't find any sinks, which can be a breeding ground for microbes. And the lighting, it's incredibly controlled because these reproductive cells, which normally live in complete darkness inside the body, are extremely sensitive to stress from light. Okay, so let's shift from the things you can see to the elements that are just as vital but totally invisible. We're talking about the air inside the lab, which has to be purer than pretty much anywhere else on the planet. And here's where it gets fascinating. Think about it. An embryo in a dish has none of the protective systems our bodies have. It's totally exposed, completely vulnerable to these airborne chemical contaminants called volatile organic compounds, or VOCs. And these things can come from the most ordinary sources imaginable: paint on the walls, cleaning fluids, floor glue, even the perfume someone might be wearing. So, to fight this invisible threat, labs follow incredibly strict air quality standards. Just look at these grades, from D all the way up to A. As you get closer to where the most critical work happens, the number of allowable particles per cubic meter of air just plummets. I mean, we're going from millions of particles all the way down to just a few thousand. That grade A level, the absolute cleanest, that's reserved for when the embryologists are actually handling the eggs and embryos directly. And this is the primary tool for creating that grade A environment, the Class II biological safety cabinet. The genius of this machine is all about airflow. It creates this constant downward flowing curtain of perfectly sterile, HEPA-filtered air. It's called laminar flow, which just means the air moves in these smooth, parallel layers, not in chaotic swirls. This sterile air bath is constantly washing over the workspace, protecting those delicate samples from literally anything floating around in the room. So, we've secured the environment. Now let's look at the high-tech heart of the lab, the equipment that basically serves as a safe haven for embryos during their first, most critical days of development. The incubator is, you could argue, the single most important piece of gear in the whole lab. And labs have a really critical choice to make. On one side, you've got the big, traditional models. They're incredibly stable. They use a jacket of water to hold their temperature rock steady, even if the power goes out. But they house a lot of patient samples all together. On the other side, you've got these smaller, benchtop models. These guys isolate each patient's dishes in their own little chamber, which means the environment recovers faster when it's opened and there's less risk of cross-contamination. The trade-off? They're way more vulnerable to a power outage. So the lab has to weigh that stability against individualized security. And this brings us to a question that I think causes huge anxiety for patients and clinicians everywhere. With so many different samples being handled, how can you be absolutely 100% certain that there is never, ever a mix-up? Well, the answer is technology. Instead of just relying on two people double-checking everything manually, which is always vulnerable to human error, modern labs use electronic witnessing systems. Every single dish, every tube, every catheter gets its own unique digital ID, like a barcode or an RFID tag. Then, at every single critical step, the system forces an electronic check. It becomes physically impossible to move forward unless the right sperm, egg, and embryo are all matched to the right patient. It creates this truly unbreakable digital chain of custody. Okay, now let's zoom in even further. We've talked about the room, we've talked about the equipment. Now we're going inside the culture dish itself. We're going into the liquid environment that is the embryo's entire world for its first few days of life. So inside that dish, a couple of physical properties are just non-negotiable. The first is osmolarity. Now, in simple terms, that's just the concentration of all the salts, sugars, and nutrients dissolved in the liquid. It has to be controlled with insane precision to perfectly mimic the environment of the fallopian tube. And here's the crucial detail. This measurement changes with temperature. Now you contrast that with osmolality, which measures the concentration by weight, not by volume. And what's the key difference? It is not affected by temperature. This makes it a way more stable and reliable measurement for the lab to use when they're first making and quality checking the media at room temperature before it ever goes into the warm incubator. To keep this delicate balance perfect, the little drops of culture medium are covered with a layer of highly purified mineral oil. This oil acts just like a protective blanket. It stops evaporation, which would throw off the osmolarity, it helps stabilize the temperature and pH, and it shields the medium from any last airborne contaminants that might have snuck past all the other defenses. For decades, IVF labs all over the world operated with a pretty fundamental flaw, a real mismatch with human biology. They cultured embryos in a standard atmosphere which has about 21% oxygen. It was just the way it was done. It was the accepted practice for a long, long time. But here is the massive breakthrough. The oxygen level inside the human reproductive tract is not 21%. It's way, way lower. It's actually closer to 5%. Realizing this and then shifting to low oxygen incubators has been one of the single biggest advances in modern IVF. It directly led to higher success rates and more babies being born. It was a total game changer. So finally, let's look ahead. The future of IVF seems to be moving in two directions at the same time, making the technology even more powerful, while also making it way more accessible and affordable for people all over the world. And that accessibility piece is a massive issue. All of this incredible technology we've just been talking about, well, it comes with a pretty hefty price tag. As this quote points out, the lab itself can account for more than half the entire cost of an IVF cycle. And that financial barrier just puts this treatment completely out of reach for millions and millions of people. So to tackle that exact problem, some innovators came up with this truly remarkable low-cost culture system. I mean, just look at this setup. It completely gets rid of the need for an expensive incubator, for medical-grade gas tanks, for all the complex air filters. Instead, it uses two simple glass tubes. One holds the culture medium, and the other generates the CO2 it needs from a simple chemical reaction. It's absolute genius in its simplicity. And the incredible thing is, it actually works. This graph shows the proof. Within just a few hours, that simple little chemical reaction creates and maintains a perfectly stable, low-oxygen environment with the ideal CO2 and pH levels. It perfectly mimics the conditions inside an incubator that costs tens of thousands of dollars for just a fraction of the price. Other new technologies are trying to make the lab environment even more dynamic, more like the human body. So instead of letting an embryo sit in a static drop of liquid, new systems can gently rock them, or use these tiny microfluidic channels to constantly bathe them in fresh medium. The goal is to wash away waste products, just like what happens naturally inside the body, or what scientists call in vivo. And this constant drive for perfection leaves us with a pretty profound question. For decades, the goal has been to perfectly replicate the in vivo oxygen environment. As we get closer and closer to actually doing that, moving from a static, good enough environment to a dynamic, near-perfect copy, we have to ask ourselves, what new frontiers, both biological and ethical, will this mastery over the first moments of life force us to confront?